So yeah, intro to programming languages. I use style. Style for intro to programming languages is scheme and lots of interpreters. So we're going to be writing interpreters today. To do this, we're going to use pmatch as a helpful tool. This is for pattern matching and scheme. Real simple. That's all the code. It's going to help us out. So we're going to start with by just loading that in.
Can you probably adjust font size?
So what?
I don't see anything. Oh, it's too little. Too small.
Oh, you need it bigger?
Yeah.
How do I adjust font size in Emacs?
6 plus.
Don't think so.
But this blue line, I don't understand.
You don't need to read that. That's just the import of pmatch.
Okay.
All the code should be readable, though. Alright, so we're just going to define an interpreter. So that's just binding the name interp, and then lambda creates a function. This interpreter is going to take an expression to evaluate an environment, and we're just going to match on what the expression is. We're going to start just by doing a lambda calculus, which consists of symbols. So if it's a symbol, then we look it up from the environment. Lambdas, which takes a symbol to bind when it later gets a value. And I'm going to leave that for a second. And the application line. So in application, we're just going to evaluate the first thing in the current environment, and then apply it to evaluating the operand in the environment. So now we're going to be using a functional representation of closures. And what this means is when we create a lambda, when we're processing the lambda, we're actually going to use our host language scheme lambda in order to represent the delay that we need to wait for the value of whatever's being passed in. And once we get that value, we will run the interpreter on the body of the lambda. And in an extended environment, which currently our environments are represented by procedures, as we can see by how we're applying the environment 2x over here. So if the symbol that's being passed into the environment is equal to the one that's bound by this lambda, we're going to return the value we got, otherwise we're going to recur on the environment. Wish I could make this fit better. So, we're going to just load this and see if it works. Since it's just a lambda calculus, we can't actually do much yet. And since our closures are represented by procedures and our environments are represented by procedures, we're going to have to pass in an environment procedure, which, if it does get applied, is just going to be an error because that's the empty environment. But since this is still waiting for a value to pass back, we're just getting a procedure and we're waiting. So we're going to add numbers. And all we need to do that is add a number line. And numbers we don't need to do anything because they're already a simple value. So we're just going to return the number back. And we might as well add booleans as well. Maybe an if line. And now we should be able to actually do some things. So obviously, if we try to interpret just a number in the empty environment, we get back the number. We can do applications. I forgot my lambda. I can't really edit those because of something weird with my Emacs I haven't figured out yet. So I need to put the lambda here so that it doesn't just evaluate the error right away. And I think I'm still doing something wrong. What am I doing wrong here? Did I never load that? I don't know. Anyway, it's getting annoying to type those environments. So we're going to make this representation independent with regard to environments, so that we don't have to deal with typing the environments out every time. So that's an empty env. If we were to extend an environment, we're just basically moving the code here for the extended environment down into here. And by making this representation independent with regard to environments, we can then change our representation of environments without changing the actual body of the interpreter at any point. And then we need to make the actual application of the environment representation independent. So that would just take a key and the environment and look up the key from the environment. So since we do that over here, we change this to apply env a env. And since we do that up here, we do that here too. So now we can do interp the x. I don't know why I put a quote there. That's probably why I was having trouble earlier. But since we now have an empty env defined, we can just do that. And to make this actually seem like it can actually do some computation, let's just define plus. Oops. So we can write, say, a function to double a number. Okay. And it works. So right now, basically, we're relying on our host language for everything. We're using our host language as plus, if, we're using our host language as procedures in order to implement our closures. Basically, we're just using our host language for everything. And since it's basically a scheme interpreter in scheme, it doesn't really give us anything. So if we wanted to make this closer to an interpreter we could actually write in C, we got to use less of our host language's inherent higher order features. And we're going to do that by making our environments data structural instead of represented by procedures. So basically, we need to move where we do these things until when we actually have all the information we need. So we're going to make extend env, just add a new key value pair for the environment onto our old environment. And I'm going to use quasi-quote to do that, which is just a list building tool. So key value, I'm just going to make that a k. And then we're just going to cons that pair onto the previous environment. So now our extend env just does it onto lists. And now all the work gets moved into apply env. And we're going to use pmatch again on the environment in order to process our environment. So we're trying to look up k from the environment we got. So if we got the empty environment, this is where we now move the error that we had before in empty-env, or we have a key value pair in the environment. We check if, and we're overloading our keys there, if the keys are equal, we return a value. Otherwise, we try again in the rest of the environment with the same current key. So we just wrote a recursive function to go down through the environment, which is now a data structure, in order to look for the value associated with a key. Now, previously, we were doing this inherently by building up a chain of functions. But now we just do it data structurally, which is something you can do in a much more low-level language. And we're just going to verify that this still works. It does, all the same. Now, in order to keep up with this data abstraction system, we're also going to abstract how we handle this closure case. So right now we're doing a lambda to delay the computation of that, but instead we're just going to skip right to a data structural representation of our closures. So our closures need basically the free variables in the expression how we were doing it before. So we do the symbol we're going to bind, the expression, and the environment. And we're just going to make a tagged list, closure, the expression, the symbol, and the environment. And we're going to delay the processing until when we apply the procedure, which will take obviously the procedure and something to apply it to. And we will, again, p-match on that procedure since it's now a closure represented by a tagged list, pull out everything we had before, and basically do what we did up here. So now, instead of having this lambda v interp, we're going to call interpret when we actually apply the procedure. And this got changed to val. We're going to add apply proc here, so that's where we apply the procedure. We're going to get rid of this lambda v, the thing we were trying to get rid of, and change it to just, we're creating a data structural closure with the x, with the current symbol, the current expression, and the body expression, and the environment. It still works. So this is all well and good, but this is not really teaching you too much about programming languages yet. So how they do that at IU is we take these interpreters and we change them to represent different features of different languages, such as dynamic versus lexical scoping, call by value, call by reference, call by name, and call by need. So we're going to change this to be a lexically scoped interpreter. And what that means is instead of looking, right now we have an environment with our closure, because when we're looking for a bound variable inside of a function, we look inside the environment at the time of that creation of the closure. So instead, we want to do it at the time of the call. So we will add an environment here at our call, change apply proc to take an environment, and then, so this is the call environment, and instead of calling the interpret of the body of the closure with the environment stored inside the closure, we will now use the call environment. And now to actually demonstrate that this does something, we have to add some more language features again, such as let makes it much more convenient to display let just a temporary variable binding, people know. But this makes it much easier to display changing the environment and then the environment inside the closure. So let is pretty simple. We just evaluate the body of the let in a new extended environment where the key is bound to the evaluated right-hand side of the let in our current environment, extended out in the old environment. So it still works, but now we have let. So if we let x be 5, x the end works. So right now we have actually already changed it to be dynamically scoped. So if we let x be 5, create a procedure foo that takes an arbitrary thing. All lambdas have to take one argument right now for simplicity, but we're just going to ignore that and return x. And then if we change the value of x to be 7 and call foo on arbitrary thing, doesn't matter, it's going to use the value of the let, since it's dynamically scoped now, the value of the let that is at the call site. So the second let is shadowing the first let, changing the value of x to 7, and when we call foo, instead of using the environment at the creation of the lambda, let the let foo where x was 5, we're going to use the x at the call site where x is 7. And I forgot to pass in an environment. So, and then we can change it back to lexically scoped just by using the closure environment instead of the call environment. Whoops. Whoops. There we go. And it's back to 5. So now it's lexically scoped again. And of course, that's where we want to keep it, because who actually wants dynamic scoping? So I'm just going to get rid of this now, since we don't want all that. And I think we already changed that use, and we don't have to pass it in over here anymore. All right. So what are people more interested in? Continuations or different call-by strategies, evaluation strategies? All right. I'm going to do continuations. Continuations are cooler. Do I have time for continuations? No, I'm going to do call by strategies. All right, so right now it's call by value, because again, the host language is call by value. And we're just taking advantage of our host language for just about everything. So in order to make this, say, call by reference, well, first we're going to need some more features in order to display what call by reference does. So if we don't have right now we're completely functional. We can't actually assign anything, so call by reference doesn't really mean anything. So we're going to add in an assignment operator and become only sort of functional. So right now what this means is we just, if we're call by value, all assignment does is add something into the environment again. So, oh, that doesn't mean anything either. Yeah, this doesn't really mean anything without call by reference anyway. So I'm just going to add an ordering operator. So this does one thing and then the other. And now when I'm going to make the thing we store into the environment be in a box. Boxes are just references. When we get back the value from the environment, we are going to unbox the thing. And then the key thing is when we actually change the value of this, we are going to look up the value from the environment. So we're going to apply env to x in the env. That's going to return a box, and we are going to set the value of the box to be whatever the value of the value of v is. And then I think we need I'll actually remember if we need that. So in call by value, we're just passing the value to a procedure. Call by reference, we're going to pass a reference to the value of the procedure. And what this means is if we mutate that variable after we passed it to a function, then outside that function we change its value as well, because it's a reference to the original value. So we are going to try to demonstrate this by setting a value here. Then we will define a function. It again takes an arbitrary thing, or it takes, yeah, I'll take a value x, I'm going to call it a, and we will set bang that a to be 7, and for now we're just going to return it after that. So now if we call foo with x, it should change the value of x I don't trust this line. Oh, I forgot the let line. The let line extends the environment. We also need to box the value we put in there because everything in the environment needs to be boxed now, so we have references to things. Okay, it appears to be still called by a value. I'm going to cheat and oops, make sure I know how this actually works. Looks right. Oh, I'm looking at the wrong thing. Okay, I think I do need this line. But we don't unbox this. I'd have to think about why that is, but since I only prepared for like half an hour this morning, it's only so much I can do. Oh good, there, now it's called by reference. This has got kind of ugly. I'm gonna write out the example over here so that you can actually see it since it's gotten really mangled by my buffers over time, but this is the example we were running. so that was the example we were just running. So in dynamic scoping, in call by reference, when we call foo, this x here is passed as a reference to this red x up here. And when we do the set bang, it changes the actual value of this to be 7. So when we come back, this x has its value actually changed. When if we were doing call by value, that wouldn't happen. And I think, okay, I have like a few minutes left.
I'm the next person. You can go ahead and finish up what you want to do.
I'm kind of just like winging it here. What
I don't know if anybody
just,
here is here yet who wants to learn about Elm, so.
I don't know. I'm kind of thinking like a lot of these people actually want to learn about Elm, not what I'm talking about. Okay, I don't know.
Go for it.
All right, I'm going to try to make this lazy. I'm going to make this call by need, hopefully, so that it actually will do it lazily and then save the value so it doesn't do it twice. Yes?
Oh, I was ready.
Okay.
All right, call by need. Okay.
Yes. That's what I hope to do. So instead of just boxing the value, because we evaluated it before we pass it in, we're just going to delay the evaluation by thunking it. Then when we look it up, we gotta unbox it and then apply it. And here we also need to make this lazy. So when we set bang a value, it doesn't evaluate it right away. When we do let, instead of extending it with the value in the let, we're going to make that thunked and evaluated. So we're just manually thunking everything like Haskell does automatically for you. And yeah, okay. So I think that should be lazy now. What's a good way of demonstrating that? Oh, right, infinite loops. All right. So if we say let x be lambda x, x, lambda x, x, and just return 5. And I forgot to pass in an environment again. Empty environment. It returns 5. Didn't run the loop. Lazy. So right now this is actually called by name, not called by need yet. I haven't done the caching, so right now we evaluate it when we look it up here in the symbol line. I'm going to make this a little prettier so it's seen more. My screen resolution and this screen resolution do not mix well. So yeah, so let's make this actually cache the value after it's been evaluated once. So right now when we just evaluate it here, we're going to evaluate it every time. But instead we're going to store it into a variable. And then we're going to change, oh actually we need, we're first going to get the box from the environment. Then we're going to evaluate that box. We're going to unbox it and apply it. So that'll get us the actual value after we've computed it. And then we're going to first change what the box refers to. So instead of the box now containing that func which has to do all that computation, we're going to change it into a new func that just contains the answer and return the answer. So that should now be called by I have to actually change the box. Yeah. That should actually be called by name or need. Yeah, need. And what I really need here is a long-running computation in order to demonstrate that it doesn't do it twice. But I am not actually going to prove that it's going to work since I am out of time. All right, any questions? Yeah?
So you check if it's a symbol first? Or?
Yeah, so basically we're just using symbols to represent our variable names.
Okay.
So the interpreter here doesn't actually support having symbols which aren't variable names. The only actual value types we support are numbers, booleans, and closures. But you can add more stuff on. But so ultimately, this is just kind of a bunch of scheme code from when I took Intro to Programming Languages. We basically develop interpreters over time, changing, doing different callbys and stuff, instead of switching between a bunch of different languages, demoing how those individual languages do things. And then eventually, this representation independent stuff, changing everything into data structures, goes on to make it very non-reliant on the host language of Scheme. And we do various, a several-stage correctness maintaining transform process and turn it into C code that interprets Scheme. Which is pretty cool, but I don't have time for that.
Does anyone there like SML or use SML?
I don't think so.
Okay, because that's the interpreters I wrote for my classes were in SML because my professor writes an SML compiler. So
oh, cool.
Language.
Yeah, no, we do Scheme a lot because we have we used to have Kent Dipvig who wrote Scheme compiler. Anyway, I'll let the next speaker talk because I'm already way over time.